Good morning. Unfortunately, I can't be giving you the lesson today. So instead, I've made this recording, which you should follow along using the pack that you've been given at the start of this lesson. So on the screen, you'll see the first of these packs, the first page of this pack, which has the checklist. And this will be one of the tasks you'll need to do after we've completed this video lesson. You'll need to go back and rag rate this checklist to see for yourself how confident you feel for each of these different aspects that we'll be looking at. Today's lesson is about mains electricity. So this is the electricity that comes from the plug in the wall. And we'll be seeing how this is different from the sort of electric circuits and electricity that we're used to with batteries. We'll also be learning about how the electricity gets from the power stations to your house using something called the national grid. Remember that on your pack, as well as having the knowledge banks at the front, you have this sheet that gives you some basic facts related to this topic, and it also tells you some of the things that you might be asked to do in the exam. So starting with the first task in the lesson, it's a little bit of a recap task, and what you're asked to do is calculate the resistance of the live wire. And I want you to do that now, and you have 30 seconds. Okay, so this is going back on what we saw with series circuits. So we've got two components, the lamp and the resistor. They are in series. And one of the things we know about a series circuit is that the current is the same anywhere in a series circuit, which means the current here is 1 amp and the current here is 1 amp, which means the current here is 1 amp. So the current through the lamp the current in the lamp is equal to 1 amp. We're told that the voltage of the cell, or the potential difference of the cell, is 3 volts, and the current is equal to 1 amp. And we can use that to work out our total resistance. So we know that we can use V equals I times R, which means in this case 3 is equal to 1 multiplied by the total resistance of my circuit, which tells me the total resistance of the circuit is equal to 3 ohms. In a series circuit, the total resistance is equal to the sum of the resistances, so we add them together. So that means that we have 3 ohms is equal to this 1 ohm resistor plus the resistance of my lamp. Therefore, the resistance of my lamp is going to be equal to 3 minus 1, so that equals 2 ohms. Okay. Right, we're looking at mains electricity, which comes from the plug, and I've said that it is different to the electricity that we get from a battery. And in the electricity from a plug, what we see is that the potential difference, rather than being one single value, like 3 volts, as we saw in the slide above, it changes. So here that we have mains electricity, it looks like this. So instead of being just one single value, for example 3 volts, it starts at 0, it goes up to a value then it goes down to another value, and keeps going up and down like this. If we looked at what the voltage would be from that cell, it's always 3 volts. So this is the voltage from a cell. So this is DC, and this is from a cell, and that, for example, could be 3 volts, which is what we saw in the question above. So we say the following. To describe the fact that the voltage changes in equipment, we call this alternating current. So mains electricity is an alternating supply, and it's at 230 volts. So something like a battery might be 3 volts. The mains electricity is 230 volts, which is what makes it so dangerous. If we're talking about the current in this circuit, if I'm using mains electricity, we call that alternating current, or AC, and we can say that the potential difference alternates, so it's alternating potential difference. In the cell, which is fixed at 3 volts, that's not alternating, it's not changing, so we call that direct voltage or direct current. So here we have, this is what it would look like for my cell. So this is known as direct current and direct potential difference, meaning it doesn't change. Okay, so we've seen that mains, it's different because it is alternating. It's not at a small voltage, 3 volts. It's at a very large voltage, like 230 volts. And we have that in an AC supply, the potential difference alternates. Now, alternates means it goes from negative to positive and back again. Positive to negative and back to positive. Okay. And what that means is that the positive and negative sides of the supply switch around. So we saw when we did the IV characteristics, to get negative potential difference, we had to swap the connections around to the cell. So here it starts as positive, so one side of the power supply is positive, and then that side becomes negative, and then it goes back positive again. This AC voltage means that the current in a circuit with AC supply is constantly changing direction. The electrons are flowing one way around the circuit, and then they're flowing the opposite way around the circuit. In a DC supply, the potential difference does not alternate. So there is direct voltage, which produces a direct current, and a direct current is a current that's always flowing in one direction, clockwise or anti-clockwise. Okay. Now moving on to the next page. So we see that the AC, the potential difference, goes from positive to negative, and the current changes direction. But we'd like to know how quickly that happens. And it actually happens extremely quickly. So we already saw that the mains potential difference value is 230 volts, so a very high voltage, but it also has a frequency, that is how quickly it changes every second, of 50 cycles per second, or 50 hertz, meaning it goes from positive to negative 50 times every second. So this is changing very, very rapidly. It's alternating extremely quickly. Now, this is what a main circuit could look like. It looks very much like the cell question that we saw above. So in the cell question above, we have the cell, resistor, and a lamp. And here in the main circuit, I've got, this is my mains power supply. Unlike in a battery or a cell, the symbol for a cell, remember, is like this. This is the positive side, this is the negative side. But here there's no positive or negative side because the positive and negative side are always switching around. Now there are two wires here. There's one connecting this side of the power supply to this side of the lamp. And then there's a second wire connecting this side of the lamp back to the other side of the power supply. And those have particular names. This one is known as the live wire, and this one is known as the neutral wire. And they have different jobs. So in the live wire, its job is to provide the alternating potential difference from the power supply. So it's what's giving the alternating potential difference. So this live wire is at 230 volts. That's what the job is of the live wire. The neutral wire has got a different job. So the neutral wire, its job is to complete the circuit so that when we have this alternating potential difference of 230 volts, the neutral wire is there to complete the circuit so the alternating current can supply. But its potential difference is zero. So the current will flow from the live wire through to the neutral wire, but it will change direction. So it will be going this way at one point, and then it will be going back the way at another. Okay, now I've said before that we know that 230 volts is a very large voltage compared to a battery. In a battery at say 1.5 volts, it's very unlikely you'll be electrocuted because the potential difference is so small. But 230 volts is a large enough voltage to be dangerous for people. And so we want to see why, in particular, it's dangerous to touch electrical circuits and plugs. What is it about this that makes it dangerous? Now you need to remember that current only flows when the circuit is complete. So the job of the neutral wire is to complete the circuit so that current could flow. So here I've shown the circuit, but I've put in a switch, and the switch is open, so the circuit is not complete. So this seems to suggest that there would be no danger in the circuit because the switch is open. Remember, the live wire is at 230 volts and the neutral wire is at 0 volts. However, in these type of circuits with mains electricity, the live wire is still dangerous even though the switch is open. So again, take 30 seconds and make an attempt to think about why might it be that the live wire is dangerous even though the circuit is not complete. Okay, so what's happening here is that when the switch is open, no current is flowing through the circuit. However, the ground that this person is standing on, is also 0 volts. So remember, the neutral wire is there to allow current to flow through the live wire and then through the neutral wire because it is 0 volts. But this is also 0 volts. So if the current can't flow through the neutral wire because the switch is open, what the current can do is flow through the live wire, then flow through the person to go to this 0 here in the ground, which means we have very high current flowing through the person. And this is why it's dangerous. Now, some appliances, some electrical machines are more dangerous than others, and metal appliances are particularly dangerous. If there's a fault, a live wire might touch the metal casing. So remember, we saw before that we had to be careful not to touch the live wire because then current can flow through us and into the ground. Here, we're not touching the live wire, but we could touch the metal casing, which is the outside of the appliance. So that could be something like, for example, something like a metal kettle or something like this type of metal angle poised lamp. These, because they're made from metal, if the live wire touches these, then the metal is conducting, is conductive. So if there's a fault, the live wire could touch the metal casing, and then we would get the metal casing goes to 230 volts. If the live wire, touches a bit, if the live wire touches the metal case, the metal casing. Notice I didn't use the word it there, guys, because if I use the word it, the examiner mightn't know if I meant the wire or the casing. The metal casing now has a voltage of 230 volts. So touching the casing in this case is the same as touching the live wire. Current could flow through us to the ground. And this is happening because the metal is a conductor. Okay, right, next section. There are then devices that have plastic casing. So what I'd like you to think about is why is it, and write down, why is it that this is not a problem, it's not dangerous, if the live wire touches something that's got a plastic casing? Why would that not be a problem? Okay, so plastic case is an insulator. So it does not go to 230 volts even if touched by the live wire. Okay. Here I've done a little picture of this situation where we have something like our kettle that has the live wire and it's connected, oh sorry, in this case it's the lamp. No. So this is my angle poised lamp and it's got a metal casing around the bulb, and which is what's shown by this box drawn around by that. And I see that I've got an extra wire that I've added, which is called this earth wire. Okay, so I've added a third wire. I don't need this earth wire to make the circuit work. I just need my live and my neutral. but I've now got this earth wire. So in this case, if there's a fault and for some reason the live wire was to then touch the metal casing, which means the metal casing is now 230 volts and dangerous, and I try to touch it, instead of current flowing through me, current is going to flow through this earth wire into the ground. So we've got this special wire, low resistance wire, and the current is going to flow through the earth wire rather than flowing through the person, which makes it safer. Okay, so how does the earth wire make it safer? Safer because if there is a fault, current will flow through the earth wire rather than flowing through the person. And this is why we have 3 pins on our plugs, because we have these 3 wires. This is what a plug looks like if you open it up. What we see is we have a connection here for a wire, so a wire can connect in here and it's held in place with a screw. And this is for the live wire, and it's connected to something called a fuse that we'll look at in a couple of minutes. This one up here is for the wire that's called the earth wire, which means that this one over here is for the neutral wire. Now, one thing that you have to be able to do is you have to be able to explain what each of these wires are for and what colors they are. And the colors are very important. It comes up a lot in exams. You need to learn them off. So these are the colors. The earth wire is the only one that's got 2 colors, green and yellow, which means that for people who have difficulty distinguishing color, so people who have some sort of color blindness, this is the only one that has the 2 colors on it. The neutral wire is shown as blue and the live wire is brown. And you have to remember those colors. So the earth wire, green and yellow, the live wire is brown, and the neutral wire is blue. Apologies for that. Right. Now, then you had to explain the function of each wire in the plug. You had this already in your pack from earlier. It's to repeating. So you do this in black pen. What's the live wire? What's the neutral wire for? And what's the earth wire for? And then use blue pen to improve your answer using the notes from earlier in the lesson. And this is a question that you can do after the lesson is completed. We also have the possibility of some plugs, they only have 2 pins, they don't have 3 pins. So they only have the live and the neutral, they don't have the earth. So here, I want you to explain why it is, what is special about some appliances that don't have an earth wire while others do. Why might it be that some don't have an earth wire and others do? Here's an example. So the hairdryer doesn't have an earth wire, the toaster does. Okay. And once you've looked at that, you can go back later, look on the OneNote and check your answers, which I'll put to the side. Now we're going to think a little bit more about the earth wire. So the earth wire is there to protect us. So if something was to happen, current is going to go through the earth wire, and current goes through the earth wire because it is very low resistance. So what we want to know is how much current is going to flow. The earth wire has to be low resistance, so the current goes through it, not us. So for example, 1 ohm. The live wire is at 230 volts. So if a fault occurs, how much current is going to flow? So that's what I want you to calculate now. And again, you have 30 seconds to do this. remember all four steps. Okay, so step one is always to write out what we know. So step one, we have the voltage is 230 volts, the resistance is 1 ohm, and we're looking for the current. There's only one equation which has those three things, V equals I times R, and substituting in, and remember that is a mark, I get 230 is equal to whatever the current is, so I write down the letter I, multiplied by 1. That is 1 mark in an exam, but it's only a mark if you write the whole thing. Next step is where I do the calculation. If I might have to divide through by this number, but in this case it's 1, so it's very much easier. So that gives me 230 amps. 230 amps is a very, very large current. Okay, the maximum current you would be using in the science lab would be maybe an amp or an amp and a half. This is 200 times larger than any current you would see in your science lab. We need to think about why this might be a problem. And think about this in terms of the current being the electrons moving through this wire, and you think about what the electrons are doing as they move through the wire. Okay, so the large currents means there is a high transfer of energy to the wire. This means the wire becomes very hot. This is happening because of the collisions of electrons with the atoms in the wire. The wire becomes very hot and can melt. Okay. It could cause a fire depending on what else is inside the device. Okay. So this is dangerous. The earth wire could melt, and also this could be a fire hazard. So the device explodes and we could get a fire hazard. So this brings us on then to the fuse. So in order to understand the fuse, remember the fuse was this part of the plug that was connected to the live wire, which has put a circle around here. This is my fuse. And why would we need that? Well, we've already seen that the earth wire has very low resistance. This is so the high currents, the alternating currents, flows when there is a fault. So current, let's write this in here. So alternating current flows in it when there's a fault and not the person. That's the most important thing. We definitely need the earth wire, and we need it to have low resistance to keep the person safe. However, this large current can damage the appliance and is dangerous for people because it causes wires and components to overheat, potentially melt, potentially catch fire. A fuse is this little sort of cylinder that's beside my live wire. It's got a small wire inside that melts when current above a certain value passes through it. So when this wire melts, the circuit is no longer complete. So live wire is no longer touching the metal casing of the appliance. So the current stops flowing and our device doesn't melt. So we need the earth wire to keep people safe, and we need the fuse to make sure that the appliance doesn't melt. Okay, now I've given some examples here. For each of these, we need to decide which of these fuses I'm going to use. They have a power, they're giving us the power, and the power is equal to the potential difference multiplied by the current. And remember, for this question 3, you need to think about this is plugged into the mains electricity. All of these are plugged into mains. So what is the value for the mains alternating potential difference? And that is 230 volts. So we use that value for potential difference. Okay, so we're going to have a little bit longer for this. We'll have 1 minute for this. Off you go. Remember the 4 steps for each of these questions. Okay, so the answer will be on OneNote, so you will be able to check your answers on there.